And an announcement that there will be a quiz next week, not this week, but next week on Schoology. It will be on dissociation, which you've already learned, versus dispersion, which is something we haven't learned, but we're going to learn this week. It will be on the difference between ionic compound solutions versus molecular solutions, and the difference between an electrolyte and a non-electrolyte. Okay, so let me just see here. And just something to keep in mind is that dissociation, I wrote everything that goes together in the same place. So dissociation goes with ionic solutions and it goes with electrolytes. Dispersion, which we're going to learn about today, goes with molecular solutions and it goes with non-electrolytes. So that will be helpful, and yeah, good stuff. So we're going to do a demonstration of an electrolyte versus a non-electrolyte. And as I said, I would have done this for you in school, but I'm at home and I don't have a conductivity apparatus. So here we're going to go watch this professor.
The term electrolyte is a term used when talking about solutions with water as the solvent. We'll demonstrate the property of being an electrolyte with an electrical conductivity tester like this. Pure water does not conduct electricity. I will put the electrodes of the apparatus into the beaker of water. There's no light coming from the light bulb. If I dissolve a material in this water and the light lights very brightly, the dissolved material is called a strong electrolyte. As an example, here is a small amount of table salt. I'm going to add just a little bit to the water and stir it up. As it dissolves, the ions of sodium and chlorine, which are charged particles, go into the water, which will now allow the solution to conduct electricity. So the ionic substance, table salt or sodium chloride, is a strong electrolyte. The term non-electrolyte refers to a substance which dissolves in water but does not allow electrical conductivity. Here is some sugar, which I will dissolve in the water. As the sugar dissolves, the light does not light up, so sugar is a non-electrolyte. Some acids and bases are also strong electrolytes. Here's an example of some hydrochloric acid. Only a little bit in the water, and about 10 drops will allow the light to light up very brightly. So the acid is also a strong electrolyte, therefore it's called a strong acid. Acetic acid, on the other hand, dissolves but allows very little electricity to go through the water. See how the light bulb gives off much less light with a lot more acid. Thus we call acetic acid a weak electrolyte, and it is a weak acid.
Okay, so we this year are not going to worry about strong electrolyte versus weak electrolyte. We are only going to distinguish between a non-electrolyte and an electrolyte. And in order to do that, we're going to take a little look at the difference between them. So ionic compounds are going to be the ones that produce electrolytes, and molecular compounds, those are very covalent compounds, are going to be the ones that produce non-electrolytes. So let's go look at the dissolving of some compounds here. Okay, so what we're going to do is we're going to take some iodine and we're going to dissolve it into water, and that's going to come up, the little picture is going to come up over here. So let's take a look. Here we go. Here's some solid iodine. Okay, and you see the molecules are made up of I2. In each of those molecules, there's an I bonded to another I. The bond within that molecule is anyone know what kind of bond we have between the I and the I? What kind of a bond is there between the I and the I? Sorry?
Covalent?
That is a covalent bond.
Yeah.
Yes. And when we put a substance into water, covalent bonds are never broken. Okay. But you can see down in here, I2 actually isn't very soluble in water, so only a little bit of it will dissolve and a lot of it will stay undissolved. And in between each of these molecules, what's holding those molecules together? Like what's holding the molecules to one another?
Molecular bond?
Yeah, intermolecular forces. Yeah, your IMFs. Okay, so there are intermolecular forces in between the molecules, and then within the molecule there are covalent bonds. And when the iodine dissolves in the water, it's those intermolecular forces that are breaking, but you'll still see the I2 is still intact, so it does not break apart. On the other hand, if we go to an ionic solid, bases just happen to be ionic solids. Here's sodium hydroxide. Here's our solid. And you see, as it goes into the water, it splits up into the sodium and hydroxide ions. And this one is completely soluble, and they are free moving. Okay, and do we have another one? Yes, we have an acid, and I don't really think we touched on acids. But hydrochloric acid, when it's not actually dissolved in water, it is a gas. It's not a solid. So let's watch it go into solution. There are some hydrochloric acid molecules. And when they dissolve, it splits apart into hydrogen ions and chloride ions. So the difference between an acid is that it has ions in it, and those ions can move. So that is called an electrolyte. The ionic compound also had ions in it, and those ions could move, so that is an electrolyte. But the iodine, remember, it didn't have charged particles. It did not separate into ions, so there's no charged particles. And to conduct an electric current, you need charged particles that can move. Okay, so let's go look at the dissolving of solid sugar, for example, because you remember that professor dissolves some sugar. And so let's go take a look at what actually happens at a molecular level when we're dissolving sugar. Go big. When the sugar is added to the water molecules surround the sugar crystals. Due to the strong attraction between the polar water molecules, that means water has a positive and a negative end, and the polar sugar molecules, which means that sugar molecules actually have little bit positive and negative bits sticking off of them. So in here, each of these little clusters is going to be a molecule of sugar held together by covalent bonds, but there might be little positive and negative areas on that molecule. It's as though maybe if you were a molecule, maybe your elbow would be positive and your knee might be negative or something like that. So there's little positive and negative bits on the sugar that can be attracted to the positive, negative ends of the water. And since the water can attract those polar sugar molecules, they can pull them apart. As the outer layer of sugar molecules are pulled away and surrounded by water molecules, the next layer of sugar molecules in the crystal are exposed to the water. There they go. Eventually, all of the sugar molecules are separated from each other and surrounded by water molecules, and the sugar is dissolved. However, each individual sugar molecule is still intact. So we don't call this process dissociation, because when we had sodium chloride, for example, and it dissociated, that meant it split apart into ions. The sugar molecules are not splitting apart into ions. In fact, they're not made of ions. They're made of neutral atoms. And so the sugar molecules simply disperse from one another. If you think about the word dispersal, just means to scatter. Okay, so all the sugar molecules that were stuck together, they just scatter within a solution. Dissolving of salt. There we go.
When an ionic substance, such as sodium chloride, is placed in water, water molecules interact with the ions on the surface. If the salt is soluble, the attractive interactions with water molecules overcome the ionic attractions within the lattice. The solvated ions move off the surface and become separated in solution. Notice that water molecules cluster about the anions with the hydrogens directed toward the negatively charged ion. On the other hand, water molecules interact with the positively charged cations through the lone pairs of electrons on the oxygens.
Okay, so what we're ending up with is we are ending up with the interactions between the water and the salt are able to overcome the interactions between the salt ions, the sodium ions and the chloride ions. Okay.
I have a quick question, Miss Spence.
Yes, certainly.
So in going back to the animation that was shown earlier, isn't it like the ions, like are they like grabbing like the ions from the solid?
Yeah, the water is grabbing the ions from the solid. That's exactly what it's like.
And isn't the ions like taken from like isn't it like just completely dissolved after the water molecules take the ions?
Absolutely, yes.
Okay, that's much better.
Yeah.
Now.
Okay.
Thank you.
Okay. And now once we know that the ions are all split apart, actually, let's just try one more because I think this one was also good. It didn't have a voiceover, but it was pretty nice, I think. How Salt Dissolves in Water by Omar Erkid. It's just 1 minute, so it shouldn't be too bad, except for I'm not playing. There we go, play. Here's a water molecule. Green is hydrogen, blue is oxygen. Here's a salt crystal. Red is chlorine, so that's going to be negative, and yellow is sodium. The blue, oxygen, and water is negative. The sodium ion is positive, the chloride ion is negative. Here comes some waters. They interact, the positive ends of the water grab onto that negative chloride, and they pull it away from the crystal. Here come some other water molecules. This time, the negative oxygen pulls on the positive sodium and pulls it away from the crystal. And eventually, the entire crystal would be just dissolved, completely dissociated. Now, what does that have to do with being able to conduct electricity? Well, let's take a look at how a light bulb lights up when you have an ionic solution. Okay, so we've got, you can see, a sodium chloride solution. Okay, you can see that down here. Well, let's see. Down in here, we've got a sodium chloride solution, and up here is a light bulb. Okay, and right now the switch is off. And electrons are going to move in the wire. Okay, that's how a current flows, is that electrons move in a wire. But within the solution, there's no free-floating electrons. So what's going to happen is that these ions are either going to move one way or they're going to move the other way. And look what happens. Eventually, all of one charge ions move one way and all of the other charged ions move the other way. And in the process, watch what happens to the light bulb. Here we go. They move, and why is the light bulb not lighting up? Oh my God, okay. It's really hard to find a good video of this.
Imagine you can see the charged particles in solution. There are sodium ions, which are positive, and chloride ions, which are negative. The others are present in water, positive hydrogen ions and negative hydroxide ions. These different charged particles are all free to move. Once the power supply is switched on, the positive ions are attracted to the negative electrode. The negative ions move towards the positive. Sodium and hydrogen.
Okay, this goes on, it talks about the whole electrolysis process, which you don't need to know about, but that's how they move. You can see that over on our left, we have the negative
Are all free
electrode.
to move. Once the power supply is switched on, the
Here's the
positive
negative
ions are
electrode on the
attracted
left,
to the negative electrode.
and on the
The
positive
negative ions
electrode is on
move
the right.
towards the positive. Sodium.
And it's the movement of those ions that is the current. Okay, and that'll be huge important in grade 12 because we will be looking at the electrolysis of a solution, which is coming up next. Okay, so what can we do with all of this? Well, we have learned the difference between dissociation, which is what the ionic compounds do, and what acids do, and dispersion, which is what the iodine did and what the sugar did. The molecules stay intact, but they actually separate from one another. So ionic compounds dissociate, molecular compounds disperse. And when the ionic compounds dissociate, they make ions, free-floating ions, so they form electrolytes, whereas molecular compounds just disperse as neutral molecules, and so they will not conduct electricity. Okay, so we're going to now take a look at this here. Okay. Electrical current is the flow of charged particles. Now, in a metal wire, what are these particles? In a metal wire, what are the charged particles that are moving? Yes, absolutely. Those are the electrons. But remember, in a solution, there are no free electrons. All the electrons are attached to other things, and they're not metals. You don't have like a solid metal in there, so solid metals are the only sorts of things that have free electrons that can move. So in a solution, what are the charged particles that are moving? It's not electrons. Who is moving in solution when you have a solution that conducts electricity?
Ions?
Those are the ions, yes, okay? Because remember, you would have NaCl, for example, which is solid, and it would dissociate, split apart into Na plus and Cl minus. And those ions are free to move about, okay? When ionic compounds and acids, that's one category, dissolve in water, the dissolving substance breaks up into, what do they break up into? Ionic compounds and acids dissolving in water, they break up into, okay, it breaks up into ions. So these are free to move around. Remember, they are free floating, and therefore they will conduct what? Electricity, yes. Electricity. Excellent. So we are now going to define the term electrolyte. An electrolyte is a substance that conducts electricity due to the presence of freely moving ions. Okay, so it is a substance that conducts electricity. That's one key point. Okay. And the reason that it conducts electricity is because it contains freely moving ions. So if I were to ask you for a definition, it would probably be worth 2 marks because you would need to say, hey, it conducts electricity. And also, it is due to the presence of freely moving ions. And if I said, give me an example, well, we could do that. We could have an example, which would be aqueous ionic or something compounds. What's the other one in addition to ionic compounds? Aqueous ionic compounds or aqueous, what's the other kind of compound that dissolves to give us those freely moving ions? So do we have, if we want to have an electrolyte, something with freely moving ions, we can dissolve an ionic compound in water, or what else can we dissolve in water?
Molecular?
No. Molecular ones, remember, they don't split apart into ions. They simply disperse. So a sugar molecule stays intact. Shoot. Okay. Acidic. Okay, so if you have an acid, it also splits apart. So you've done a bunch of dissociations of ionic compounds. Today, we're also going to look at dissociations of acidic compounds, because even though acids are molecular, they will dissociate into ions in water. It's because the hydrogen ion is so teeny tiny and it falls off easily. We're not going to worry too much about why, but anyway. Okay, so our next question, which of the following solutions will be electrolytes? Will it be an ionic compound, a molecular compound, or an acid? Which of the following solutions will be electrolytes? Acid, yes, very good. Anything else? When we dissolve sodium chloride in water, do the sodium ion and the chloride ion stay together, or do they separate? So here's a sodium and a chloride ion. Are they going to stay together in the water, or are they going to separate?
I think they'll probably be they'll remain there, but they'll probably be split.
Yeah, they're going to be split, so they will separate. Okay. And this process, what's the process where sodium and chloride split apart in the water? What's that process called? Starts with a D.
Dispersion?
Dispersion, you're really close. It is a dis. Sadly, they're both disses, so they sound similar. Decomposition, that's a good guess. Dissociation, yeah. Dissociation, yeah, okay. All right, and the solution that is produced by the dissociation of those ions, will that solution conduct electricity or not conduct electricity? Yes, it will. Okay, and we're going to draw what happens to the sodium chloride crystal when it dissolves in water. So I'm going to make that a little smaller. And should I keep them together or, well, I'm splitting them apart, right? So I should have my chloride ions, 1, 2, 3, 4, 5, 6, chloride, 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 chloride. And I'm also going to have my 6 sodiums, which are a little bit smaller. 1, 2, 3, 4, 5, 6. And I'm just going to label them with a plus because I don't really have room to write sodium in each of them. Okay, so I have a 1-to-1 ratio of 1 sodium ion for every 1 chloride ion. And these ions are free floating. So this one can move around. The chloride can move around. Everybody's all moving all the time. All ions moving all over the place. Over the place. Okay, now was that a chemical change or a physical change? And this actually, I'm going to give you the answer because this one is a little confusing. It seems like they're coming apart, but really, if you taste solid salt, it's going to taste salty. If you taste aqueous salt, it's going to taste salty. The properties are the same. If you evaporate the water, you'll get salt back. So the salt has not changed into any different substance. The salt is still salt. So this is a physical change. Okay.
So basically means it's just reversible, Miss Spence.
It's reversible and there's no new substance.
Only chemical changes is the opposite.
Yeah.
And it can't be changed,
yeah.
Perhaps.
Okay, and so we could write what kind of equation would we write for this? This starts with a D. We're going to write the
Dissociation.
Dissociation. Yes, very good. The dissociation equation would be NaCl, solid, goes to Na plus aqueous plus Cl minus aqueous. Now, I've learned that I can distribute this page to your classroom notebook. So in Teams, you're going to be able to look in your classroom notebook. And I think it's in the notebook. There's a tab at the top. So rather than me having to make a PDF of this, I think you can access it through the classroom notebook. What I'll do is I'll put it in there and you guys can let me know. If it doesn't work, then I will make a PDF of this and send it on out to you. Okay. Now, remember we had our solid iodine and we have the I, which is bonded to another I. That's a nonmetal and a nonmetal. What kind of bond is that in the middle?
Covalent.
That is covalent. Can water break covalent bonds?
No.
No. So when the I2 dissolves in water, the two I atoms, do they break apart or do they stay together? They stay together, yes. Okay, and so this is not going to be dissociation. Dissociation is when the ions separate. In this case, there's no ions and they're not separating. So instead, this is another D word. It still starts with dis. What do we call it this time? Not dissociation, but
Dispersion.
Dispersion, yes. Okay, and so the solution, well, let's see what happens when we draw the solid iodine. You can see that there's individual iodine molecules and there are intermolecular I wrote molecular
That's better.
Forces between the I2s and they break. So what would it look like when we have I2 in the beaker? What would those particles look like? Well, because they're not breaking apart, I would have an I and an I, and I would have another I and an I. It's not working very well. I need a smaller font. There's an I and an I and I and I. And I think maybe what I'll do to make them look like they're actually stuck together is I'll go like this. Me. Okay, there we go. That's minorly better. So this is I2, and now it is aqueous. We went from having I2, which is solid, to having I2, which is aqueous. And this process was known as dispersion. And the equation for dispersion is really, really silly. It's like crazily simple. So the dispersion equation is, we would have I2, which is a solid. And then when it dissolves, it doesn't do anything. It's still I2. It's just now it's not solid, it is aqueous. What's the charge of these particles? These I2 particles are electrically, are they positive, are they negative, or are they neutral? They are electrically neutral, yeah. Okay, and so let's see, the I2 particles are electrically neutral. And so will this conduct electricity?
Not at all.
No. So this is a non-electrolyte because there's no charged particles. So if I were to stick my conductivity apparatus in there, the light bulb would not light. Okay. All right, now when hydrochloric acid dissolves in water, the H plus and the Cl minus, now remember this is an acid, okay? And acids are a little strange. They are a molecular compound. It is a covalent bond that holds them together. However, H plus is a funny little ion. It's a tiny, tiny little positive ion. And the Cl is a great big negative ion, and chlorine pulls electrons to itself really strongly. So if I had a couple of electrons here in between the two, they would actually not hang out with the hydrogen very much at all. They'd be very strongly pulled towards the chlorine, which would mean that the hydrogen, it's easy for it to fall off. Do you need to know that for grade 11? Well, if we had a full year, yes, we would, but you don't need to know it this year because it's a weird year. So what you do need to know is that the H plus and the Cl minus will actually separate, even though it's a molecule. And this process, where our HCl splits apart into H plus and Cl minus, what do we call that process?
Dissociation?
That
Because
is
you're dividing into ions. Separate.
Exactly, that is dissociation. Okay. And will the solution produced conduct electricity or not? Yeah, it will conduct because we have those ions. And just so that we get the whole meal deal here, we know that we have HCl. It's a gas when it's not dissolved in water. It's not a solid, so this is HCl gas. But when it dissolves in the water, you're going to have H plus ions, which I can't draw the H in there, they're too small. And we will have the chloride ions, which are going to be much bigger. And again, these ions can move. The ions are moving all the time. So if we all get them going in one direction, if all the positives go one way and all the negatives go another way, then we have electrical current. Okay, I'm going to rejig our what I thought we were going to do, because as always, it took longer than usual. So I think if we go back to what I said would be on the quiz next time, well, you know what? I'm not going to put this stuff on the quiz. No. There. Can you guys just wait for the assignment to see what's on the quiz? I'm going to change it up a bit for the assignment to see what's on the quiz. I'll be able to organize my thoughts a bit better. What's on next week's quiz? Remember, that's next week, not this week. Week's quiz. To prepare for that quiz, you are going to do, your homework is going to be, number one, to do the witchy witty who. The blue.
I thought you were going to tell us to finish the rest of the.
Yeah, the blue questions, the rest of the formula equations and complete ionic equations.
So is it just like saying problems? Is it the one saying problems for each of the following reactant combinations and
exactly,
and so on and so on?
Yeah, formula equations.
Like I did all 14 questions. Am I safe for now?
Yeah. Net ionic, complete ionic, and net ionic equations. Now, we're at 45 minutes, but if anyone would like to ask questions about that worksheet from last week, this would be a good time to do it.